and if you put r prime equals to half, it gives you an S matrix which allows for maximum power dissipation. Okay? And when the voltage configuration corresponds to that, is that you ground one of them, put minus voltage on one, put plus voltage on one, you can normalize it, which basically tells you that you're pushing in unit power, and that will give you, that will tell you that you generate a non-equilibrium distribution which can be completely equilibrated on. All the power is dissipated on. Okay? So essentially it tells you that it's a nice characterization of your circuit. Okay? You can put voltages, it's a completely non-equilibrium thing, and you can characterize your circuit. So it basically tells you that r prime equals to half is an S matrix which is very different than any other S matrix, where you cannot tune this. You cannot have a complete dissipation. Okay. So now, what are the good conditions which this M matrix should follow? So the good conditions are rho must add up to 1. This gauge invariance, which essentially amounts to saying that if you increase the voltage on each of the terminals, you shouldn't have any change in any physical quantity, right? So that will be ensured by the fact that the rows of the M matrix add up to 1. The columns must add up to 1. That tells you charge must be conserved. It's basically Kirchhoff's law. You must have the incoming current must add up to the outgoing currents. And the third thing is your eigenvalues must be bounded between 0 and 1. Otherwise, you will have more dissipation than the power use. So you can have a situation where you sent in a power and you dissipate more than what you sent in. That cannot happen. So that will be bounded by this eigenvalue bound condition. Okay, so if you put all these conditions, then this is something which is satisfied by any underlying theory. It doesn't matter if it's interacting or not. If you have a free theory, of course, it will be satisfied. Even if you have an interacting theory, this cannot be violated. So it doesn't matter what your theory is. If it is a one-dimensional channel, for example, so what should I compare with what? So let's say you take the nu equals to 1 case, which is a free fermion case, and then you take the nu equal to 1/3 case, which is the interacting case, right? So one corresponds to a free electron theory, one corresponds to interacting electron theory. For both of them, essentially the M matrix have to respect this condition. There is no choice. Okay? So it's a way of, so if you in an experiment, if you can figure out this M matrix, it gives you a lot of information about that state. Okay? So what are the M matrix which are allowed? So what you can do is you can ask the following question. So now we convert the question into something else. Initially I was talking about maximum power dissipation. Now we'll talk about zero power dissipation. What are the M matrix which are allowed if you have zero power dissipation? So let's take the 2×2 case. If you take the 2×2 case, so what you can immediately see is that all you need from this relation is that your M matrix has to be orthogonal. If it is orthogonal, M dagger M is 1, no dissipation. Okay? So all you need to look for is conditions where M dagger M is orthogonal. So what are the cases in which, so rows should add up to 1, columns should add up to 1, and the eigenvalue should be bounded between 0 and 1, and they have to be orthogonal. So in 2×2 case, there's only two possibilities. Either you have perfect reflection or you have perfect transmission. That's true. You know that even if you switch on interaction for Luttinger liquid, there are only two fixed points. Either you have perfectly reflecting fixed points or perfectly transmitting fixed points. So it doesn't matter your theory is interacting or free. These are the only allowed non-dissipative situation allowed by general principles. You don't need to put in any more details. Now I can ask this question: what happens if I take a 3-terminal case? Does it change? It actually changes quite a bit. So you see that these are both orthogonal, parameterized this way. These are two different one-parameter family of M matrix, each of which corresponds to a dissipation-less situation. There is no dissipation. So which are the ones which I can rationalize from a free fermion theory? These are the ones which you can rationalize from a free fermion theory. You can only put zeros and ones. You see you have a 3×3 matrix, and it has to be all real inputs because it's a current splitting matrix, and rows have to add up to 1, columns have to add up to 1. The only way to do this is put ones and zeros if you want a free fermion theory, because I can construct a S matrix out of it. Just take a square root of these guys, put the appropriate sign, it will be a right S matrix. Okay? So now this M matrix is a situation which corresponds to say that it's a disconnected wire. You have 3 wires where there is perfect reflection. Very trivial. The other case is a time reversal broken situation where you have perfect transmission from 1 to 2, 2 to 3, 3 to 1, and this corresponds to this one. So these can be described both within free and interacting theories. It's obvious that this belongs to the free theory. But what about the rest? The rest essentially corresponds to a situation which are strongly interacting cases. Okay. So there's a 2 one-parameter family of M matrix, current splitting matrix, which essentially correspond to interacting theory. Who tells you that it's actually a valid interacting theory which can be realized in nature, right? You can cook up mathematically whatever you like, but who tells you that this is really a valid theory? So what you can do is that you can take interacting theory, which is essentially Luttinger liquid theory, take the case of nu equals to 1/3. So if you take the case of nu equals to 1/3 and ask yourself, so let's take you take this geometry and ask yourself, what are the all possible boundary, if this was nu equal to 1/3 edge, which is an interacting edge, what are the all possible M matrix I can put here? It will turn out that if you start with the tunneling Hamiltonian and really look at different strong coupling limits of your different all possible perturbations, it will take you to this family of S matrix, M matrix, which are nothing but all possible conformally invariant boundary conditions which you can put at the junction. Okay, so this is really consistent. It's coming from a very different point of view. You see, I'm not trying to bosonize things. I'm not trying to do anything. All general arguments, 3 arguments: charge conservation, global gauge symmetry, and orthogonality. That's all I said. And it doesn't matter what the underlying theory is. What I'm claiming is you can show that all these things can be shown as a fixed point of a legitimate theory. Okay, that's what I'm saying. So now, when this thing was proposed, actually this came up first in Oshikawa, Shimon, and Affleck, and then we followed it up with a proposal for in the quantum Hall context with Diptiman and Sumate. And later on also we showed that in certain cases these fixed points are extremely interesting. Actually, we all know that in Luttinger liquid, because it's interacting, there's a suppression of tunneling density of states. But it turns out that you can find certain fixed points here which show enhancement of tunneling density of states, which is pretty counterintuitive. But they are hosted here. Okay, so the point is now, what experiment can you propose? These set of people had a certain proposal of experiments. All these experiments essentially amount to saying that go and measure power laws. Who wants to measure power law? Nobody probably. It's very difficult to measure power law. Given this geometry, you can't convince any experimentalist to really measure power law. So now what I'm saying is the following. You don't have to measure power law. Just do the following. Make a four-terminal measurement. So take this device and put some injecting current here and put some voltage probes in all of the outgoing channels. Measure the four-terminal voltages associated with each channel, which you can do for both interacting and the free theory. In the free theory, it has the interpretation of the chemical potential. In the interacting theory, it will have the interpretation of the zero mode. Zero mode is still fermionic. You have bosonic excitation, which are particle Hurl excitation. It doesn't matter. When you measure the voltage, it is nothing but the zero mode which you measure, which is pretty fermionic. So now you can measure that quantity. And if you can measure these two quantities, you can reconstruct the M matrix. And once you reconstruct the M matrix, then you can just, whatever you measure in an experiment, you can now ask how close am I to any of these guys. And if you find your M matrix measured from experiment close to these guys, you can actually show how close you are to the fixed point. Okay. So this will be my proposal of how to really go about measuring this fixed. Yeah.
You have a line of fixed points?
Yeah, 2 lines of fixed points actually. Yeah, this is the first one and this is the second one.
And how do you relate them to interaction? Why is it that a non-interacting system can realize?
Oh, so this is you can imagine these have to add up to 1, and you don't want to put zeros and ones, so you can't. So what will be the typical way of getting, like if you have a M matrix, you will say take square root of all these guys, and that will be the probability amplitude, right? You can't do that to negative numbers. Some of these M matrix can have corner splitting matrix with negative numbers. That's what will happen actually. These are more like Andreev reflection, but this is happening due to interaction, and it's not happening due to some superconductivity. So you can have negative. Of course, you will have negative numbers there. There is no other way to satisfy it. If you don't have negative numbers there, you will have just ones and zeros there. So that's the whole point. Yeah. Right. So this is what you can show is that, yeah, of course, what you can show is that you can start from here and switch on the appropriate perturbation, which are essentially some tunneling operators there, and take the strong coupling limit of those tunneling operators. They will drive you to the fixed point, and I'm saying that these are the families of fixed point which they will drive you to if you take all possible perturbations in the theory. That's what I'm saying. Huh? I'm saying that I'm claiming this. This is there in our work. I can sit with you and show that how it works out. But if you take all possible perturbations, then you can show that this is the only possible fixed point which you can hit. You can't have anything else, because anything else will be inconsistent with charge conservation. Actually, there is one fixed point which is missing here, which was said in Affleck and this Affleck's work, Affleck and Oshikawa and Shimon's work, which is called a dissipative fixed point. They showed that you can have a conformally invariant boundary condition even in a dissipative condition, and that is something I don't know how to get there. So this family of fixed points which I show here comprise of all possible boundary conditions except for one, which I don't know how to parameterize. How much time do I have? Oh, geez. Okay. So, okay, fine. I think I'll kind of. And how much can I stretch? Okay, fine. So what I'm trying to argue is that by measuring this M matrix, which seems to be a measurable quantity now, you can do a lot of more things which you could not have done before. So that's the first part of the proposal. And what he showed with my student is that you can even show that for an n-terminal geometry, if it is a free fermion theory, then you can show that there is a perfect correlation between the. So in an n-terminal geometry, of course, Each terminal has its own noise. So you put all possible voltages on the terminals, and what you can do is you can measure noise on each of these terminals. Now, you measure the autocorrelated noise, sum it up, it gives the total noise in the circuit. Now, you can also measure, by measuring these voltages, you can measure the total dissipation associated with your circuit. And what you show is that the total noise is completely correlated with the total dissipation. Okay? And where is that expression? I don't find it, actually. Looks like. No. I think it's coming. Here it is. So what I show is that if you have n-terminal geometry, this is our proposal. If you have n-terminal geometry, what you can do is first you can have a voltage probe associated with it and measure these voltages, and you know, of course, what are the incoming voltages. Given these two information, you can essentially measure these quantities and use our formula to get one number, which is the dissipation in the circuit, the total dissipation. Then you can chop off this one and essentially do some noise measurement here and measure the noise on each terminal. And if I sum the noise up, what you will see is that the total noise measured and the total power dissipation is essentially related by this relation. Okay? So the total autocorrelated noise and the total power dissipation is essentially connected by some voltage which you apply, and that's a universal number. That's it. Okay, so let me go to the next part of the story, which is essentially so the motivation of understanding all these things is associated with the fact that if you want to use heating in your device for understanding some physics like exciting neutral modes, then you must understand how does the heating happens and what it can do to your circuit, right? So that was a simple starting point, but that is where we want to get. We want in a complicated edge theory with a complicated circuitry, you want to understand how heating works. So what I will do here is basically tell you about few. Do I have that much time? So maybe I'll just tell you about one quick experiment, skip all of this, which was done by Abik actually in the Weizmann group, in Moti Heiblin's group, and then go ahead to our proposal. So what was done in this experiment, this is an experiment which was done to probe the neutral mode in the 5/2 state, which is supposed to be a non-abelian state. So essentially there were two most strong candidates for this state, which is one is called a Pfaffian, another one is called an anti-Pfaffian. Probably there are others also. So these were the most popular ones. And the difference between them was the following. So one state has a charge mode and a neutral mode co-propagating with each other. And another one had a charge mode and couple of neutral modes. One charge neutral mode, which was bosonic, and one Majorana mode, flowing opposite to each other. So the primary thing which I want you to follow is the following. So you have two situations. So this is the 5/2 state. You tune your magnetic field to the 5/2 state, and there are two competing candidates. One is the Pfaffian, one is the anti-Pfaffian, the particle-hole conjugate of each other. And the way they differ is each of them has an edge mode, but the edge mode has different composition. In one case, you have an edge mode co-propagating with the neutral mode. In another case, you have an edge mode counter-propagating with the neutral mode. So what this experiment did is what they took is a contact here. So this is a QPC here, and you take 4 contacts. There are three important contacts. This one, and maybe there's a 4th one, which is also very important. Yeah. So these are the 4 important contacts. What you do is you try to inject current here, and you can inject current in such a direction such that the charge mode is going this way and the neutral mode is coming that way. Okay. So essentially, if you push current here, all the current will be taken out in a terminal there, which is grounded. Okay. So essentially, this current never goes to the QPC. What goes, if you wish, is essentially an excited neutral mode. So essentially, you drive current here, heat up this contact. This hot contact heats up the neutral mode. Then there's an excited neutral mode which runs to the QPC, and something happens in the QPC. Nobody knows what happens. Then what you do is start measuring noise here. Okay? So of course, if you are essentially injecting a neutral mode, what you do not expect is to see any feature in the charged noise. But it turns out that as they started cranking up the voltage here, actually the noise measured here had a strong feature. The noise increased with the cranking of the voltage. Okay? That's the interesting point. So all the charge is going here and getting dumped there. It's going out of the circuit. What is coming back most likely, if it is anti-Pfaffian, and if it is a Pfaffian, of course, there is no reason you should see any signal here. If it is an anti-Pfaffian, then probably what is running down here is the neutral mode. If the neutral mode is running down here, there is a hot neutral mode running down here, and it's doing something. God knows what it's doing, but whatever it is doing, finally, there's a measurement here, which is a charge noise measurement, that shows a signal. So essentially, as you crank up the voltage here, you see the noise goes up here. That's the observation. So that immediately tells you that given the direction of the magnetic field, of course, you know which direction the charge is moving. Okay? So you know for sure the charge is going that way. So the only thing which can happen is neutral is flowing that way. So that was the conclusion of this story. Now, the interesting point is, what you start asking yourself is that, so if I'm really heating up this channel here, why don't I see, the natural question to ask is, why don't I see thermoelectric effect? Essentially what I'm doing, I have a QPC, I have an edge state here, I have another edge state there. This edge state is hotter, this edge state is cooler. So what I should do is, if I heat this up, I should see a current response there. But they never see any current response. They heat up this thing, and they keep heating up, but it only changes the noise. Which tells you that somehow the system has a perfect particle-hole symmetry. So the QPC is, like, people believe that the QPC has a lot of energy-dependent transmission and so on. But this experiment tells me that even this ugly QPC, which is probably sitting in a complicated 5-half state, doesn't look like there's any particle-hole symmetry breaking, which basically means that it has no energy dependence. Okay, otherwise you could have seen a current here. You don't see a current here. So the next question which naturally comes to your mind is, why don't we break particle-hole symmetry? How do you do that in a controlled way? Very simple. You just plug in a quantum dot. You plug in a quantum dot here, which basically a bunch of levels. And now, if you get tuned the levels, if you're able to tune your levels, then essentially you break particle-hole symmetry in a desired way. You can exactly go to the Fermi level. If this is the Fermi level, you put your level here. You have perfect particle-hole symmetry. You go above, you go below. You break particle-hole symmetry. That generates current, and essentially that's equivalent to saying you convert the neutral signal into a charged signal. So that was our proposal. So that's what we did with Adi, and we told Moti about this story. And he just did the experiment in 2 months, which was, I think, quite amazing. Right? That's correct, right? After he told him it was done in 2 months, almost like that. We had to compete with him to finish the paper, actually. Otherwise, his paper would have come out first. Anyway, so that's... Yeah? Yeah, it says something about that. Of course, it says we were highly non-local, right? And the interactions were very weak. Yeah, I think. Oh, okay. So can I take a... Thanks. Okay. So that's what you do. You plug in a quantum dot, and then you repeat this whole experiment, and what you expect is to see some current response, and that's precisely what they see. So let me skip all the details of our calculation and show you something which they see. So this is what they see. So this is the current response of the device. So there's a nice peak here, and exactly... Yeah. This is the geometry. This is a very simple geometry. You heat here, there's a quantum dot, and you measure. That's it. So first of all, they see the standard Coulomb bouquet, and then they go ahead and basically thermal bias it. So first they normal bias it. If you do the normal biasing, you essentially see the Coulomb blockade peaks, and then once you thermal bias it, what they see starts seeing thermoelectric response. What you expect is a response like that, but they don't have sensitivity to the direction of current, so those see a double peak. So essentially the expectation is where the current peaks, if you look at the thermoelectric response, so maybe I just draw it here, what you expect to see is something like that. The current should go to 0 exactly at the particle-hole symmetric point. It peaks here just sidewise and peaks there on the other side, right? So if you do not have the sensitivity to the direction of current, what they measure is essentially this double peak. So it basically means that this is being flipped over here, and you see peak here, and you see that it's completely consistent because wherever they see the current peak, exactly there they see a dip here, 0 current there. So that's what they see. And our proposal actually, so this experiment was done in the metallic regime. And so first part of our proposal is just put in a quantum dot and you don't have to do anything. Close your eyes and you should see the signal, right? But of course, you want to ask also, what more can I see by plugging in a quantum dot? So what more can you see is maybe I kind of summarize here in the blackboard. And this should take 2 more minutes, or maybe -2. So the situation is the following. So I must confess that this experiment was not done for the 5-half state. It was done for the 2/3 states, and they are yet to do it for the 5-half state. But the 2/3 state and the 5-half state have the same character in the sense that both has a counter-propagating charge and a neutral mode. Okay, and the prediction which he made further is that you can essentially characterize these states if you look at the details of the thermoelectric response. And how do you see that? So the way to see that is if you have a certain degeneracy of your quantum dot. So essentially what will happen, so imagine that you have a single level, and that's coupled to the Fermi liquid leads, the simple resonant level. Then what you can think is exactly at 0 bias, then this level will be half occupied and half filled, right? Because if you are in steady state, this has a certain, so let's say the occupied state is 1, unoccupied state is 0, and exactly in steady state is half filled and half empty. So essentially you will see a peak in current exactly when your state is half filled. Now imagine that there's a degeneracy in the problem. There's a many-body degeneracy in the problem due to whatever reason. You have two states here. Then, of course, you have state empty and the state where the first one is filled, the second one is filled, right? You have more states now. Now, of course, in steady state, again, all the states will be equally filled, which basically means each state will be 1/3 filled, right? So essentially, what it amounts to saying is that at steady state, this state will be 2/3 filled, and it will be 1/3 empty. The moment that happens, we know that the current will be maximum exactly when it's half filled. So essentially, the current peak shifts because of the degeneracy. If you see the shifting of this peak, from there you can have a measure of the degeneracy. So essentially, it turns out due to the CFT which lives in the boundary, different CFTs have different degeneracies for putting in an electron. As I told you that for the anti-Pfaffian, there's one neutral mode and there is a Majorana mode, okay? And the charge mode goes opposite. So you can break the neutral mode into 2 Majorana fermions. So essentially you got 3 Majorana fermions. And now you can imagine that there are 3 ways to make an electron. You can stick in this one with the electron operator. You can stick in this one with the electron operator. You can stick in this one with the electron operator. That makes it 3-fold degenerate. So essentially, there are three degenerate levels for plugging an electron into the dot. So essentially, the degeneracy is a direct measure of the CFT which lives in the boundary. Okay, and that can be measured by simply looking at how much this peak is skewed. Okay, because what happens is that once your current peak shifts, so as I said, you have a current peak, and then there is a thermoelectric peak, which is essentially something like this, right? Now, if this peak shifts, essentially it skews your thermoelectric response, and the measure of skewness is essentially a measure of this degeneracy. So you can know exactly what CFT lives in the boundary simply by looking at its skewness, but all you have to do for that is go to a limit where you have a small quantum dot. And Moti has a metallic quantum dot. He's yet to reach that regime. I think with that I will stop here.
Thanks a lot. Maybe we can take 1 or 2 questions, if there are.
Yeah.
How you analyze your fixed point here? Kindly tell me.
Okay. Which one? I don't know which one are you talking about?
The first part in which you are two matrix you call it.
So I have to, like there's a whole family of perturbations which you can write down. And once I write down a perturbation, then only there is a question of writing down a RG equation for its amplitude, right? So I never wrote that down for you. No, of course we have done the RG equations, and it's there in Oshikawa and Shimon and Affleck. Really did a comprehensive analysis of this RG equation. We also did to a large extent, but their paper is like a Bible. You can just look it up there. All the perturbations are written down very correctly there. Yeah.
Okay, so let's thank the 2 speakers again of this session. And Shorin, here is some memento for you.
Thank you. Thanks.
And we break for tea, coffee now, and then half an hour, I suppose, we come back for the 3rd lecture, Shankar. Group photo, yeah. So please assemble outside the department for the group photo.